Next topic, Hardy-Littlewood Maximal Inequality. So one important definition is Hardy-Littlewood maximal function. Okay, given f a measurable function, of course we are discussing everything in terms of Lebesgue measure. So it's a Lebesgue measurable function. For a given Lebesgue measurable function, one can define this Hardy-Littlewood maximal function as follows. Consider at a point B we define as this. So look at the integration of this f, the lambda. I am using lambda for Lebesgue measure. I am looking at the Lebesgue measurable function, and I am defining Hardy-Littlewood maximal function at the point B. So look at b minus t and b plus t. So integrate the function between b minus t and b plus t, and the length of the interval that we are evaluating is 2t, so divide by the length, and hence it is the average value of this function in the interval minus b by t to b plus t. And now take the supremum all such positive quantities. Okay, and this is what we call it as, we define using the star f star of b, and this is defined for any b in R. So what this definition says, it's the average value of the function in the interval b minus t to b plus t, and look at the supremum of this average values for all positive values of t. Let's quickly look at a few examples. Suppose f is constant function, then can you see that the integration of this interval is just the length of the interval, which is 2t, and if I divide by the length 2t, it becomes 1, and this is true for any positive value of t, and hence f star is also constant. Let's also look at, suppose f is given to be characteristic function on 0 1, then let's look at geometrically and try to understand this. So the function is the point b, then look at that b minus t and b plus t. Then the integral between b minus t and b plus t is going to be just length into the base length 2t into 1, and if I divide by the 2t, you will get 1. Okay, and hence the inner expression is going to be 1 as long as t is smaller than b minus t and b plus t falls into this, and if it goes out, it's going to be a smaller number, and hence the average is going to be 1, and hence, so for b between 0 and 1, f star of b is going to be 1. So if I consider b on the negative side, and as long as if b minus t and b plus t are on the left of 0, then the integration is going to be 0, and hence corresponding to all those t, the integration value is 0, hence the expression, supremum of expression is also going to be 0, and hence we should get into the interval 0 1. Okay, let me try it again. So for the case, if my b is here, then if I consider b plus t and b minus t, then for the same function, this time we will get this length, this area. This happens only when your b plus t is less than 1 and bigger than 0. The third case is b being on the right. In this case, this should have this length, this area. Corresponding to this case is your b minus t has to be between 0 and 1. Of course, one can include the end cases also. Okay, before going further, what this Hardy-Littlewood maximal inequality is going to say, remember we have already done this. So in comparison to this what we call it as Markov inequality, here the same thing we are going to consider. The Hardy-Littlewood maximal inequality says look at all those points for which the f star of x is bigger than c and bigger than c is less than or equal to 3 by c times so this measure. Okay, so it gives something similar, but the estimate is slightly 3 times more. Okay. So let me state. So the Hardy-Littlewood Maximal Inequality Hardy maximal inequality says the following. Suppose f belongs to L1 of R, then this set, the set of all B belongs to R such that your f star of B is strictly bigger than C. Is less than or equal to 3 by C times norm of 1. We will prove this Hardy-Littlewood maximal inequality in the following way. First, if I want to prove Lebesgue measure of any set, we already know that it can be approximated by closed set from inside, which is called inner regularity, and hence we prove the following: given any closed subset of this set, then the measure of that set is less than or equal to whatever we want on the right hand side. Consider a closed subset, closed and bounded. Remember, we have proved this not only inner regularity, kind of compact. You can approximate within by compact sets and outside by open sets, which we call it as inner regularity and outer regularity of Lebesgue measurable sets. Of course, one has to prove that why this is a Lebesgue measurable set. That immediately follows if we prove that f star is a measurable function. We started with this closed set. See what we will rely on. We will exploit this compactness of f. We will first get a open cover for f. So let B belongs to f, this closed set. Since it is inside this right hand side set, f star of B is bigger than C, and hence there exists a T positive by the definition of supremum, such that your C is integral B minus T to B plus T, of course 1 by T, the CF d lambda. So let me also just rewrite this. This is equivalent to saying that 2TC is less than now. Is it clear that your f is subset of all this kind of T, whatever we got? Let me denote this with the suffix TB. So corresponding to each B you got a, so f minus TB and B plus TB, and to take union of all B from F. Okay. And note that these are all open sets and it's an open cover, and hence since F is closed and bounded, it should have finite subcover. So call that finite subcover as this is going to be subset of B1 TB1 B plus TB1 union Bn minus TBn Bn plus TBn. This is by compactness of F. So this is by compactness. Okay. Now using Vitalis, what we could get is that the disjoint open sets such that it is 3 times some BK1 minus of corresponding DP1 and BK2 plus TB2 union BK minus TBM BKM plus TBKM. Okay, so M of such sets, of course 3 times, where each of these sets are disjoint. So BKI, this collection, minus TBK1 is a disjoint family and finite. Now we are all set to go ahead to prove. Now the Lebesgue measure of F is less than or equal to 3 times length of this interval by this definition, which is 2TB1 2TBK2 plus 3 times 2TBKM. Now use the fact that we have proved that this information, okay, since C is positive, we can always write this to be 3 by C times of 2CTBK1 plus 2CTBK2 plus 2TBKM C. Okay. Now go back to the inequality that we have, 2TC. This is true for every B and corresponding TB that you get, and hence this is less than or equal to 3T times in the interval BK1 minus TBK1 to BK1 plus TBK1 of the function F. And same thing with the last term, BKM minus TBK1 BKM minus TBKM plus of the F. This is the expression that we get. But notice all these intervals by the choice of Vitalis lemma, they are disjoint, and hence this sum has to be less than or equal to minus infinity to infinity. That's the overall F. And that is what we want. So we get 3 by c times norm F of 1, and that proves Hardy-Littlewood maximal inequality.